Hello again. So here we're gonna wrap up our four-part lecture on integrals, and this time we'll be talking about notation finally, and we'll also get this idea of definite integrals introduced. That idea of definite integrals will actually really blend into the next lecture, um, and so that'll be a sort of a natural shift out of just, hey, here's the basic idea of integrals and let's get into the next part. So with that, let's go ahead and actually start on notation. Here's something that I want to point out. All of these are true, and they also really all say the same thing. And so we've just seen examples with x's here, where I just have, hey, integral of 2x, x squared plus c, great. But nothing says that we have to use the letter x. I mean, I could use the letter a, I could use the letter t, I could use a dollar sign if I wanted. I could use a smiley face. I could use whatever I wanted. And as long as the notation is sort of consistent throughout, that's what's important. And so I'll just make this clear that it doesn't have to be an X in here. It could be an A. But notice what changes, right? When I go from X to A or T or a dollar sign, the variable in here is sort of that. This is my function 2t that I'm taking an integral of. So my variable is t, clearly. I do change the dx to a dt, so I got to make sure that this part right here that I'm underlining matches whatever my variable is, and then my answer obviously has to match as well. So all of these are true. Variables can change in an integral. It doesn't have to be an x, but we tend to use x a lot. That's the most common, but it doesn't have to be. All right. So finally, we've seen these integrals over and over. Let's actually go ahead and get into the naming, the parts of an integral, and actually breaking down what this is actually saying. So as you could probably surmise, this elongated S looking thing, this symbol, it's called an integral sign. When you see that, it means, hey, I'm taking an integral of whatever follows it. This f of x, it's called the integrand. And so that's a word that you'll hear me say a lot, actually. I may have an integral written on the page, and I'll say, hey, take a look at the integrand. And that's me just calling out what the function is that I'm taking a derivative, or excuse me, an integral of. So that integrand is a key word that you'll hear me say. Dx is called the differential, and I've kind of just washed over why this needs to be there. I'm going to kind of continue to wash over why it's there and just point out that it needs to be there. Really, what it is it gives us an indication of what the integration variable is. When you look at this dx or dt, dA, d dollar sign, when you look at that, that's telling you what variable you're taking an integral of. Just like with derivatives, we had d dx of, like x squared. And, or actually, let's just simplify this. Like we had dy dx. That was another notation we used just for a general function y that we want to take a derivative of. But if I wrote dy dt, that can possibly mean a different thing. That means I'm taking a derivative with respect to t. And that's exactly what this x does right here and this dx does, is it lets us know that, hey, x is the integration variable. It's the variable that I'm taking an integral with respect to. So that's where the differential comes in. That's why it's important. I am kind of washing over why it's there, but that's okay for now. So parts of an integral right there, we've got the integral sign, the integrand, which you'll hear me use a lot, the differential, and the integration variable right there. So we've got that, and all said and done, this entire thing is called an indefinite integral. The reason that we call it indefinite is because it is not definite when we get our answer. Our answer is not a definitive statement. And that's because we always end up having whatever our answer is plus c. And remember that plus c stands for an infinite number of constants that you could theoretically add on to the end of this integral and it would still be correct. And so we don't have a definitive answer, so we call it an indefinite integral. we're going to contrast this with a definite integral, which when we have a definite integral, we are actually going to get a very specific answer. We won't have this plus c. Let's go ahead and look at that. So a definite integral, it's going to look very similar to this right here, but what's going to be different is I am going to have limits of integration. And so a and b here, they are constants, they are x values, and they're going to be my limits of integration. Sometimes what you'll see people write, I think I write this a little bit more often than most people. Some people will actually write x equals a, x equals b. That just makes it very clear that a and b are x values. The reason I harp on this, it doesn't really have anything to do with this lecture, but has more to do with future lectures. So a and b are limits of integration. They are x values. Really keep that in mind. So this whole thing is called a definite integral. And the question is, well, what the heck do I do with it? How is it different from an indefinite integral? Well, how it's different is that because we have these limits of integration, I have to actually do the problem a little bit differently. So let's take a look at an example because that's the best way to sort of talk about this. So I've got a simple integral of 2x dx, and I'm integrating from 3 to 7. And let me actually pause and repeat what I just said. When I see this integral, how I verbally say it is the integral of 2x dx from 3 to 7. You could equivalently say the integral from 3 to 7 of 2x dx. Either way is fine. You'll generally hear me say the integral of 2x from 3 to 7, just because when I say the integral of blank, I want that blank to be what I'm taking an integral of. So most of the time I won't say the integral from 3 to 7 of 2x. I'll say the integral of 2x from 3 to 7. A minor difference there. It's not really that important, but just explaining why I say it the way I do. So we've got this right here. And how we're going to start off is just as you might expect. We're going to take the integral of 2x, which when I do that and I use that power rule, I get x squared. But here's the difference. We're not going to write a plus c. That's bad. We don't want that here. Because we have endpoints, limits of integration, 3 and 7, I may call those endpoints every once in a while. So because I have endpoints, what I actually am going to do, I'm going to evaluate x squared at 3 and 7. And the notation here looks a little new, possibly. It's a bar with a 7 on the top and a 3 on the bottom. This right here, if I look at, so I'm going to box this right here, and I'm going to read this out verbally. X squared evaluated at 7 minus x squared evaluated at 3. And notice there's no minus sign anywhere in that box, but that's what this means. This bar means, hey, take what precedes it and evaluate at these numbers that are there. So just for a little aside, let me go ahead and write some stuff out here. I might have something like 6x cubed, and I could say evaluate at 2. You'll notice there is not a top number up here. I didn't put anything there. And in that case, what I do here is I take 2 and I plug it in to my function, which then gives me 6 times 8, 48. And if I write evaluated at, I don't know, 5 and 2, if I put both of them there, then what I do is I evaluate at the top one first, and then I subtract the evaluation of the bottom one. And so then we have a little bit more work to do here. 5 cubed is 125 minus 6 times 8. 6 times 125 is 750, if I'm doing that math in my head correctly, minus 48, 702. There we go. And so just a difference right here where, oh, erased on accident. Just a difference here in sort of notation. This bar means evaluate. If I just put one number, I'm just evaluating at that number. If I put two numbers there, then I have to evaluate at each of them, but then subtract the difference. Make sure that you do the top one first here. So little bit different, a little bit new notation there, but this bar just means evaluate. Let me be very clear as well. There is a very big difference. Kind of put this off to the side. There's a very big difference between 2x plus, let's say 2x squared plus 3x evaluated at 2 and parentheses 2x squared plus 3x evaluated at 2. In this scenario here, that this is indicating that I'm only evaluating 3x at 2, and I'm leaving the 2x squared there. Here, this indicates that I'm evaluating the entire thing at 2. So make sure that you're careful about where you put your parentheses there. And most of the time, you're going to want those parentheses if it calls for it. But yeah, so there we go there with that notation using that bar. And yeah, so there we go. So coming back here, we've got x squared, and I'm evaluating at 7 and 3. Let's actually go ahead and do that. I'm going to take 7 squared. I'm going to take 3 squared, and I'm going to subtract them. And when I do that, I have 49 minus 9, which is just 40. And that ends up being my answer. And what you'll notice here, let me space this out a little bit better. What you'll notice is that there's no plus C. There's one answer here. We get a specific answer of 40. We get a definite answer, a definitive value for this integral. This integral is equal to 40, and that's it. There's no plus C. It's not, I can't change it around. It is just equal to 40 exactly. And that's why we call this a definite integral. So you'll see all that work that I just did right there, plugging in the 7 and the 3, and there we go. So when I have a definite integral, when I have these endpoints, I just start off by doing the integral as I normally would, x squared. But then instead of adding a plus C, I actually evaluate at 7 and 3 and subtract the difference there. So I could write this as a formula, if you will. It's more of a method than a formula. That's why I put formula in quotes. But it's basically just saying, hey, if I have my definite integral right here, so I've got my A and my B, I take my integral. So I go from my little f to my answer, whatever my capital F, whatever the actual integral is, and I evaluate at B and A. And what you notice is that that's just me taking this function and plugging in B, plugging in A, and then subtracting the difference there. And so there we go. This formula, we won't really harp on that too much. You're probably just going to get more comfortable with just doing these examples and seeing how the 7 and the 3, those numbers, these limits of integration sort of get plugged in. As I said that, it gave me one more reminder to mention these limits of integration here. You'll hear me refer to them as one of 3 things: limits of integration, endpoints, or sometimes I'll just say limits. Don't let that confuse you with like a limit in in the calculus sense, but don't let that confuse you in like the LIM as X, don't let that confuse you there. Sometimes I just say limits, and that's just sort of shorthand for limits of integration. And I can say endpoints as well. All right, so that's going to be part 4 of our 4-part lecture on integrals. So that wraps it all up. And we'll get into some more complicated and a little bit more application of how we can actually look at these integrals in some different lights. And that'll be it.